All right, so let's sort of pick up where we left off, or any questions before we pick up where we left off? So when I did the example last time, I had the thing moving horizontally. And I want to talk a little bit about the vertical. I'm not going to go through the full derivation of why we can ignore some things, but at least go through this one. So I have a spring that just hangs at some position right there, some initial position. We'll call it x1. I put a mass on it, and I put it into a new equilibrium position, x2. So if I look at the force diagram of that mass there, what are the forces acting on M in that middle situation?
Wait.
Yeah. Tension. Or I guess, oh, yeah, elastic.
Yes. And that's it, it's just sitting there. So the spring force must be equal to the weight, and so let's make it positive. Fs minus W equals 0, and so K x2 minus x1 minus mg equals 0.
K is our spring constant, right?
Yes.
Okay.
Let's go ahead and establish that right now. K equals spring constant. And so I have this K x2 minus x1 is equal to mg. Now in the next scenario, I take this mass, exact same mass, I pull it down and I let go. So now this thing is going to be oscillating back and forth. Again, same two forces acting on it. So in situation number 3, I've got spring force, spring force 3, and weight. It is not equilibrium. So Fs3 minus W is equal to 0. And so that's going to be the spring constant times how far the spring is stretched. And how far has the spring stretched? Oh, I didn't actually label.
X3 minus x2.
That's how far, in addition, I stretched it. But what is the natural position of the spring?
X3 minus x1.
Yeah, x3 minus x1. Equals mg. Now I know that mg is equal to this right here, so I'm going to go ahead and make that substitution. So I have kx3 minus kx1, distributing, is equal to kx2 minus kx1. Where's the mistake? There's a mistake in here.
Oh, of this positive.
Sorry?
Of this positive?
No, that's not the problem.
Oh, since it's moving, the spring constant shouldn't equal the weight there, right?
Yep. It's equal to mass times acceleration. It's not equilibrium.
Yeah.
It's not the fact that it's not moving, the fact that it's not in equilibrium. That's the main thing. So minus mg equals ma. So I'm going to subtract this. I know that mg is equal to kx2 minus kx1, and that's equal to ma. I can distribute that negative sign and start getting rid of stuff. So I have kx3 minus kx1 minus kx2 plus kx1 equals ma. Obviously, what can we get rid of?
KX1.
Okay, yeah.
And so what I'm left with is kx3 minus kx2 equals ma, or k times x3 minus x2. Which was part of my hesitation when you answered, Anna. This right here is just how much it's stretched from that distance right there. So we can treat it as that is the stretch right there, as long as we don't consider the weight of it. The weight canceled out. If you want to bring the weight into it, then you need to do it from the stretches from here. If we look at the energy, the potential energy, the spring potential energy, or elastic potential energy, the 1/2 K delta X squared, if you take the weight into account, in other words, you also take into account gravitational potential energy, MGH, then you're dealing with a stretch from here. If you are not going to consider the weight and not consider the gravitational potential energy, then the stretch is from here. And so in the problem I did the other day where I had it horizontally, because I didn't want to have to deal with that issue at that moment, but if I'd hung it vertically and I said I had a mass sitting on it, and then I pulled it down and let go, it would have been the exact same math problem as what we had yesterday. So now I take that mass and I stretch it down, so let's make this distance here 3 meters. Let's make this distance here 2 meters. And let's make the mass equal to 5 kilograms. Let's figure out what we can. Figure out how long it takes. I pull it down and let go. How long is it going to take to go up and all the way back down? Amongst other things. Questions before we do that?
Just to clarify, these distances are that additional bit of stretch. It's not the x1, x2, x3, it's like the difference between, like the additional amount that was stretched.
Ultimately, yeah, the additional amount. We're assuming an ideal spring. This has no mass. It's not pulling itself down. It's just naturally that length.
You said if this problem was horizontal, it would be like the exact same concept?
Right.
Okay.
Where it sits in some natural position, I pull it out, in this case, 3 meters, and let go. That's the same problem as this.
Gotcha.
Oftentimes I'll set it up, you have a spring sitting there naturally, you add a mass to it, it's in equilibrium again, and then I take that same spring and I put it horizontally, attach a different mass to it. The first part is just so that we can figure out what the value of K is,
Okay.
in essence, using this.
Mm-hmm.
It would only be the same math problem if there was no friction on the object that's attached to the spring, though, I would imagine.
If there's no friction. Yep. Yeah, because I guess in the horizontals, it's rubbing against something.
Right, like I picture like a slinky attached to a box, you can probably pull that slinky pretty far until the box would actually move, but.
Yeah, don't bring too much reality into it. This is physics. Now let's deal with the easy case first, and then we can add reality over time. Let's find K. So my spring constant times 2 meters is equal to 5 kilograms times, what the heck, let's make it Earth, meters per second squared. What is the spring constant?
24.5.
Units?
Kilograms, meters,
Is that like
I
over
don't know.
kilogram meters second over seconds per square?
Meters times squared.
It seems like there was a mess of stuff just said there. All right, so we're doing kilogram meter per second squared divided by meters.
So is it just kilograms per second squared?
Yeah, so kilograms per second squared works. Not usually the way it's expressed, but it's valid. Or 24.5 newtons per meter. Suppose I now take that 5 kilogram mass and put a 10 kilogram mass on it. What's the spring constant now?
It would have.
49?
Not 49. What did you say?
I said double.
Oh. And Brooke?
Wouldn't it just say the same?
Why?
Because it's like the mass doesn't affect the way the spring can stretch itself.
Oh, it would stretch.
The wording was off, but
It would stretch twice as much. Like it's twice as heavy, but it would stretch twice as much. So these two numbers would.
yeah. This is a spring constant. It is a constant for that spring. So adding an additional mass or adding some more here would just make it stretch farther, as was just said. Now, if I said it's the exact same length, then that's a different spring. But that value there is associated with that spring.
So it stays constant, is what you're saying. Like it's always gonna be 24.5 for this spring.
Until we somehow manage to change the spring, but yes. that spring will be 24.5 newton per meter.
No matter what the mass is.
Correct.
Okay.
Since it is ideal, in reality, yes, if I've got a large enough mass on there, that spring is gonna stretch to the point where it deforms. We are assuming no deformation, which is the nice thing about ideal. All right, so now I take my, let's keep it at 5 kilograms. I take the 5 kilogram mass, I pull it down an additional 3 meters, and now I let go. What is the amplitude of the oscillation? Because when I let go, that thing's gonna start bouncing up and down.
What do you
Is
mean?
amplitude 3 meters?
It would be. How far I stretch it from equilibrium, it should be the,
The absolute value of that,
Yeah.
right?
and so it's gonna be oscillating back and forth between these two spots right here. It'll go basically 1 meter above the spring's natural length, but it'll be 3 meters below to 3 meters above. If we make, do I still have a positive? Yeah, there it is. So my position, what the heck, let's stick with the brainwashing, y equals -3 meters. Now, times the cosine. What assumption did I make when I said, wrote down -3 meters there?
Up is positive. Oh,
Oh yeah, that's one of them, but there's another assumption that I made that I did not state explicitly.
that you're pulling it down first instead of up?
That would explain the negative.
Does that have something to do with the cosine?
No. I could have done sine here, I'm doing cosine, generally when you start at the extreme,
Yeah.
it comes 0, use cosine. If you start at the origin or the middle. All right, so what does y represent here?
The vertical, axis?
Or J hat?
Looking,
Displacement?
not wrong, but not just, what did you mean by that?
The change in displacement?
There wouldn't be change in displacement.
I'm not sure.
Position?
Position is what I was thinking of. So position is, what, let's go back to the definition of position.
Where an object is relative to its starting point?
This displacement.
Oh, sorry, relative to,
zero.
yeah.
And so as soon as I wrote down -3, where have I established 0 to be?
It's equilibrium point? At the equilibrium point?
This equilibrium point here. So I've established that to be 0, positives up, negatives down. So I'm starting at -3 meters. Times omega t plus 5. How do we find omega? If you look back at the equations we did 2 days ago,
V over R, probably not useful.
that's angular speed, this is angular frequency. Although they look and smell the same, it's not gonna help us a whole lot there.
Omega equals the square root of k over m.
And so we end up with a square root of 24.5 newtons per meter, divided by our mass of 5 kilograms.
That's our rotational frequency, is that what you said?
Angular frequency.
What do you mean by frequency? Is it like oscillating, like how frequently it oscillates back and forth?
If I have a wheel here and a peg on the wheel so that a light source from over here is casting a shadow, that shadow is going to match the movement of this mass up and down. Omega is the angular frequency of the shadow, which relates directly to the angular speed this wheel has to go in order for the shadow to match the movement of the mass. That's what angular frequency is. There are better applications in what omega does. Ultimately, if you take what we're learning about waves here in general and apply it later to electromagnetic waves, because some of it does translate quite nicely, omega is ultimately very much connected to the speed of light. So there would be the physical connection there. I know that's vague, just a teaser of what's to come.
Yeah.
Oh, anyway, what's the value?
It's 2.21.
Units? Well, since it also relates to angular speed, I don't know if that would help.
Radians per second squared? Radians per second?
There we go.
Okay.
Radians per second. Radians per second squared would be the units of
Angular velocity.
Acceleration.
acceleration.
Okay.
All right, so we now know what omega is. What about phi?
Phase shift.
Yeah, so what's the phase shift?
3 meters?
Nope.
Would it be 2 meters? Since we're phase shift? No.
No, that 2 meters that it brought it down, that'd be almost like you're changing what 0 is.
Right.
If that's the case, then ultimately you could just tack on some number here just to shift the scale up and down.
Mm-hmm. Would just be 0?
It would be 0. Why?
Because we define 0 at the like equilibrium points. So there like is no phase shift? 'Cause that's
Not the real reason why there's no phase shift. There are a couple of things in play here that would, I would contend would be part of it, but not the real reason. When do we start the clock? When this time is equal to 0? At what point? You said 12 a.m.? No, in the context of this problem.
When do we start the clock?
Yeah, when time is equal to 0.
When you release
the mass.
All right. So when time is equal to 0, if we say time is equal to 0 at release, what is the position at release?
-3.
So the phase shift, I got -3 cosine of 2.21 t plus phi. That's my generic equation there. At time is equal to 0, this becomes y is equal to -3 times the cosine of 2.21 times 0 plus phi. You just told me that this is equal to -3, so -3 equals -3 cosine, that's 0 plus phi. What is phi so that this is true?
0.
Yeah. By starting this at an extreme, by starting out with an amplitude of, with our convention of where 0 is and up being negative, by making that -3 and starting time at the moment of release, using cosine sets phi equal to 0. If this had been a sine, we couldn't get away with that. Phi would not be 0. All right, but the question I'd asked before was, how long does it take to go up and down? So let's see if we can get there. So we have this angular frequency here, but we also have frequency. Frequency is how often something occurs. So frequency, number, I guess, cycles per second. If we think about, let's go back to the wheel here. The angular frequency deals with how fast this thing is spinning around, or the angular speed, which relates to the shadow moving up and down. Frequency we have this repetitive motion of this wheel going around and around and around. Frequency would be how often this spot ends up back here. So if in one cycle takes a certain amount of time to happen, so the frequency would be 1 over the period, because the period being how long it takes to go around once. The angular frequency is equal to the angular speed of the wheel, and that's equal to the angle divided by time. Well, what angle does it go through once around?
360.
Let's be cool. Radians.
2 pi.
There we go. So that's equal to 2 pi over the time it takes to do that. In other words, since frequency is 1 over the period, and angular frequency is 2 pi over the period, this is just equal to 2 pi times the frequency. And a matter of fact, your textbook doesn't use omega, I believe. I think they just stick 2 pi f in there instead of omega. So therefore, since omega is equal to 2 pi times the frequency, and that's equal to 2.21 radians per second. What is the frequency?
0.3517.
And units?
Radians per second?
traditionally not spoken that way, although mathematically it is not incorrect. But it would be misleading if you wrote that,
Cycles per second?
otherwise known as, technically this is 2 pi radians per cycle, and so the radians would cancel out, that's why that would happen.
Okay.
So let me write down cycles per second. And then the more traditionally expressed version. Spoiler, hertz.
Oh, hertz.
So we now know what the frequency is. We can now predict how long it's gonna take for that to go up and down. So how do we find the period?
Would you set, you could do 1 over the period equals 0.3517?
Yep.
2.843
Second?
Yeah, seconds.
seconds, okay.
If you said second per cycle, I wouldn't take off of that. Typically, you just say seconds. The fact that it's the period, you know that's time for 1 cycle. So the thing would bob up and down. So let's see how close we can actually come to matching any of that kind of stuff. We're obviously gonna have to use new numbers. So what I'm hoping to do here, I need some platform on which to put this. It has some natural length to it. If I add a mass to it, it will stretch, and so we'll get some idea of, we'll be able to get the spring constant off of that.
Would the spring constant be different for that particular spring if you were to have hooked it like above or below the point?
Absolutely.
You are not on camera. I don't know if you
Oh.
want to be.
Oh, there's water in that too. One of these days. Hopefully enough of that's on camera. So I need to figure out where it is the initial position, similar to over there. It's almost 1 meter exactly. Probably for as close as we're gonna get, that 1 meter is probably good enough. Actually, we're within a millimeter of it, so we'll just say at 1 meter right now. I attach a mass to the bottom one. Now, as I add the mass, notice that it's now at an angle here. What I'm gonna do is measure the low side and the high side and just take the average value. I have seen students, there's a lab that deals with this. Students come up with some sort of crosshatch plan with the bottom ring so that they can attach the mass to the middle, so you don't get that wobble, but not too crucial. So that's 50 grams we've added, and the bottom of it is at 65.5 centimeters, and the top side at 70 centimeters, and that is, those distances are from the ground. So when I add 50 grams, it's stretched from 1 meter to the average of that, 67.75. So what is the displacement? How much did it actually stretch?
If you subtract 67.75 from a meter,
Yes?
33.25.
Let's stick with meters, so 0.3325 meters.
Wait, would it be
Uh,
32.25?
It would be.
Oh, that's funny. Thank you for catching.
Wouldn't that be a negative displacement? Because centimeters is smaller than a meter, and we're going downward.
To establish how far it actually, what I really care about is how far it actually stretched.
Okay.
We don't really need to worry about plus and minus right now. I mean, we can really get into that part, but I know ultimately, if I just look at the absolute value, back to the equation that was right here, we had K delta X is equal to mg. I know this is always a positive number, so I'm gonna make this always a positive number, so I'm just gonna make delta X positive
Okay.
and not worry about the really keeping track of the negative sign. There's a lot of physics, especially in 152, where you pay really close attention to the signs, or you just think through what it is and then tack it on at the end.
Okay.
So this is a tack it on at the end kind of deal.
Okay.
All right, so we can get a crude approximation here. And so, actually, let's make the prediction before we do that. If I added a 20-gram mass, how much should it stretch?
It'd be somewhere half to that, wouldn't it?
I assume half is just a ballpark.
Yeah. It'd be a little less than half.
Yeah, it should be a little less than half. How would you actually calculate it?
I did 32.25 times 20 divided by 50, just kind of doing the
Okay.
proportion. Is that?
Yep, absolutely.
I got 12.9.
12.9. So I would expect it to stretch down to, well, if we use the ground as our base, then it'll be whatever 1 meter minus 12.9 centimeters is, which is 87.1. Let's see what actually happens. And again, it's physics, so who knows?
How did you find how much it would stretch or go down?
The spring constant times how much it stretches is equal to
Gotcha.
the weight. And so, finishing that thought off, in case there was someone else with that question, the spring constant is mg over delta x. So g is relatively constant in this small little space here.
Right.
So this ratio of the mass to the stretch should be constant.
Okay. Okay.
And so the mass is 40%, so the stretch should be 40%.
Okay.
The bottom end is at 85.4 centimeters, and the upper end, I'm not getting parallax in there, it was like 89.5. So the average would be 87.45, and we had predicted 87.1. So we're 3 millimeters off. Not too bad for physics. So with a 20 kilogram mass, or sorry, 20 gram mass on it, what would we expect the period to be? I know that the period is 1 over the frequency. I know 2 pi times the frequency is equal to the angular frequency, which is also equal to the square root of k over m. So I have k, in theory I have an m. So solving for frequency, frequency is 1 over 2 pi times the square root of k over m, or the period is 2 pi times the square root of k over k. So what is the prediction? And that's the 20 gram mass on there right now. Oh, we didn't actually solve for k, did we?
The spring constant, I mean, I used the equation from the k delta x is equal to mass times, is that acceleration due to gravity or?
Yes, it is. So what'd you get for k?
1.52. And it wouldn't change due to the different masses, right? Because we're still at the same,
K should not.
yeah, okay.
In a lab situation, you would actually do maybe 5 different masses, get the stretch, and then look at the slope. Base it up, the k value does on the slope.
Gotcha.
We're cutting some steps out.
So it's 0.72
0.72 what?
seconds.
Yes. Let's see how close we actually get with that. Now, how much do I need to pull it down? How does the amplitude affect our answer over there?
How does it affect our frequency?
Yeah, or period, or any of those. Any of the math that we just did over there,
Well, what if it's,
any of that, how does the amplitude affect it?
well, it's a greater, if it's a greater distance to travel, then that impacts the frequency.
Where does that show up in the math?
K equals mg over displacement, so if you have a bigger displacement,
Yeah, but that is, I'm actually putting mass on it, finding new equilibrium. The amplitude is how far I stretch it from this new equilibrium spot.
Is it because the spring is a conservative force, and so it's moving the same speed at the same point? So if you stretch it further, it's moving faster, but it's also moving faster at the top, and so it would be ultimately the same?
Ultimately at the same time.
Right.
The speed's not the same. You started out to say it and then you quickly stopped, but just to emphasize, because if I stretch it more, there's going to be greater speed acting on it. And so even though there's more distance to cover, as Brooke, you were saying, it's offset by the fact that it's traveling faster. And so ultimately, the amplitude, in an ideal situation, the amplitude does not affect how long it's going to take to oscillate up and down.
And that's because it's an elastic force is conservative. Does that have anything to do with it, or?
That, I hesitate to take it that far, because there are other conservative forces where there is a difference between the amount of, the greater the fall, the more time it takes.
Right, right.
All right, so what we're gonna do, when you're typically doing something like this, you don't wanna just do one timing, especially at 0.72 seconds, reflexes. Although reflexes should not have a huge impact there, reflexes will have some impact there at 0.72 seconds. So we're gonna oscillate 10 times, so I'm gonna start it pushed up, and then when I let go 10 cycles. I'm gonna go 3, 2, 1, go. When I say go, I'm gonna release it, and then we'll count 10 cycles. 3, 2, 1, go. 9, 10.
13.87.
13.87.
I have 13.72.
I got 13.67.
13.65.
Pretty darn consistent there,
Yeah.
and way off of what we have down here.
Yes, sir.
So first off, what is the average?
Divided by 10. Okay, yeah.
Yeah, divide by 10, so we end up with 1.3.
7275.
So why are we so far off?
Because it's not an ideal spring.
What specifically about this not being ideal has messed it up?
The math.
Is it at an
Yes.
angle? Oh, yeah, that too.
The mass of the spring. Now what we can do here is figure out what is the effective mass of the spring. Let's assume that this measurement right here is accurate. So my period, 2 pi square root of m over k. We have 1.37275 is equal to 2 pi times the square root of 0.02 plus the effective mass of the spring divided by 1.52. And so let's find out what the effective mass is of the spring, and then we'll put the 50 kilogram mass on there, and we should come out with a much closer prediction. To Jacob's point, since you first said because it's not an ideal spring, there are several aspects of the fact that this is not an ideal spring. Mass specifically is something that we can actually adjust for, unlike some of the other less than ideal aspects.
Does some of it have to do with the fact that mass probably isn't distributed evenly with the spring, or like, because what are some of the other things that make a spring an ideal spring? Like,
It won't interfere with itself. If I pulled it down and let go, in theory, there's a point where
it would.
an ideal would never hit itself, but this one, there is a maximum it can actually go up.
Okay, gotcha.
And as well as when it stretches, the molecular bonds are being stretched out and pulled back and stretched out and pulled back. And so there's probably a little bit of heating up going on too.
Physics people really wanted to cut corners, huh?
Is this in kilograms or grams?
0.02 is in kilograms.
Okay.
What'd you get?
0.0526.
I have 0.0525, so basically the same.
Okay.
Yeah, I got that number as well.
All right, so now with this in mind, when I put the 50 gram mass on, we now have a prediction of 2 pi times the square root of 0.05 plus 0.0526, or 5, whichever one you're working with, over 1.52. Because it is oscillating not only the mass that I stuck on the end of it, but the mass of the spring itself. Ian, you have an answer?
1.632.
1.632?
Yeah, that's seconds. I got the same thing.
Same thing. All right.
It's even further though, from our 0.72. Doesn't
Right,
it-
well, we also have more mass on it.
Right.
Ideally, if you're running this experiment, are you trying to put the weight on the very end? Or are you trying to put the weight, like of the last ring? Or are you trying to put it, on like any specific?
I'm trying to put it on the last loop,
Okay,
the last ring. Because the size, if I did it here, that's a different spring constant
okay,
for that bit than it is for the whole thing.
gotcha.
To be consistent. All right, so let's get ready to time 10 cycles, not revolutions. All right, 3, 2, 1, go. 10.
16.27.
I got 16.45.
16.26.
16.17.
16.11. 252.
And we predicted 1.632, we got 252, we're off by 7,000th of a second. Pretty darn good.
Yeah. And in terms of what we're doing, what does this period tell us? We know that it tells us how many revolutions gets us
the period tells us how long it takes for it to complete its cycle.
Oh, so like until it comes to rest.
From whatever point, so if I say time is equal to 0 here, right when I release it, then it's how much time it takes for it to go down and get back to that point again.
Okay,
So the period is how long it takes for it to get back to the same point in the cycle. So beginning of the cycle to beginning of the second cycle, or middle of the first cycle to the middle of the second cycle, whatever you're doing.
okay.
In order to be able to show something's in simple harmonic motion, it has to obey Hooke's law. The spring force is proportional to the displacement from equilibrium. We can now extend that idea and find another classic and actually historically important bit, the pendulum. Now, traditionally, when you're dealing with pendulums, the angle that you're given is from the vertical, so this angle right here, theta. Now, this is known as a simple pendulum, and some of the characteristics of our nice ideal simple pendulum we've dealt with before. So, one of which, no friction, we don't have to worry about what's going on up there where the string connects, no air resistance and so forth, and then all mass is at the end. In other words, the string or whatever we're using has no impact whatsoever, no mass here. If we did take that into account, it would be called a physical pendulum, and we can deal with that math too, but then that's bringing in moment of inertia, and that's more than I want to do right now. So let's look at the forces. What are the forces acting on that mass?
Tension?
Weight and tension.
Which way is this thing going to accelerate? If I pull it out to there and let go, which way will it accelerate?
Towards the point that it's attached.
So you're
Like
that way?
centrifugal acceleration?
Yeah.
And you were pointing that way?
I was just pointing, I guess like.
In the arc that it would travel.
All right.
Yeah.
So we have two different accelerations here, because yes, there's an acceleration pointing towards the fulcrum. That's the centripetal acceleration, and then there's angular acceleration or tangential acceleration pointing in that direction.
But that ends up pointing out towards us because of the right angle. Is that right?
Angular acceleration would be out at you, yes. So I have my tangential acceleration and my centripetal acceleration. It looks like we have a great way of setting up our coordinate system right there, because fortunately they are perpendicular to each other. I hat and j hat. So what are we breaking up?
Wait.
So I know that that angle there is theta. That angle right there. I'm breaking weight up into components like that. If that's theta, that's 90 degrees. This angle right here would be the complement, and this angle down here would be theta. So I have my tension going this way. I have mg cosine of theta as, I guess in some sense, a centrifugal force, and then mg sine theta in that direction. I'm not concerned about the centripetal forces in this case. What I care about is the mg sine theta piece. Is this proportional to the negative of the displacement? So I have mg sine theta is equal to ma.
What would it have to do with the displacement of the mass?
Hooke's law, where we started with simple harmonic motion,
Yeah.
is that negative k delta x is equal to mass times acceleration,
Okay.
if we just have the simple spring. And so what we need to show, this is where we started, and then found a function that would make this work so that they were proportional and negative, and then we got the cosine equation and all the other stuff we've done so far.
Okay.
What I'm trying to get to is does this also obey Hooke's law?
Right.
And as a spoiler, kind of. So we have, the mass cancels out. So g sine theta is equal to a. This is more specifically the tangential acceleration. So one issue we have here is the fact that I've got an angular or rotational quantity and I've got a linear quantity. So we need to get those at least in the same type quantity. It'll be simpler to get this in terms of angular what is the relationship between tangential acceleration and angular acceleration?
They're the same?
As much as speed and angular speed are the same.
They have the same formula then?
Oh, it's that same thing. Oh, what is that acronym you always use?
The one I do, acronym I usually do is one for arc length and angle, but it's the
That's
same
what I think,
relationship.
Yeah,
The standing room only,
yes.
S equals r theta, v equals r omega. Tangential acceleration is equal to r alpha. In this particular case, r is the distance from that, basically the axis of rotation, which is up here. And so let's just go ahead and define this from here to here as length L. And so this is equal to L alpha. So we now have g times the sine of this angle is equal to L alpha. Now there's another mistake that I traditionally always, I think I make this mistake every single time I do this, but it is going to cause an issue. What is the direction of the angular displacement?
Towards the middle?
Not towards the middle,
Towards the point of the fulcrum.
right-hand rule.
Is it also out towards us? Right.
So equilibrium, normal equilibrium is straight down,
Okay.
and we pulled it out that way,
Oh, it's towards us.
It's in towards the board.
that way.
Yeah,
You go
because if
from
it's
one to
going
the other.
this way.
That's your left hand. Yep, right hand.
So,
If we rotate it that way.
oh, it's coming up this way.
Yeah.
I thought it was going that way. So
The angular acceleration is gonna be the other direction.
yeah, okay.
So there's an extra minus sign that I should have put in somewhere, one side or the other.
Why is angular acceleration out towards us? Like, you guys said that earlier and I got lost.
So right now it's at rest. I pull out to here, it's at rest, and I let go. So it's gonna accelerate this way.
Right? Wait,
It will accelerate, from our point of view, it would accelerate counterclockwise, which, from a vector point of view, is outwards.
I'm struggling. Wait.
Imagine your thumb's the pivot point, and your fingers are curling in the direction that it basically gets pushed.
Oh, okay. Now it makes sense.
Now, we aren't quite in that form over there. Because here we have the linear displacement and the acceleration. Over here, though, we have the sign of the angular displacement and acceleration. So we got to deal with that sign somehow. Enter the small angle approximation.
Oh, I thought that would be about to be side angle.
Yeah, but it could also be that too, but not in this context. Small angle approximation. And what it states is that if theta is much less than 1, so the less than symbol, the doubled up like that means much less than. It's a quick and dirty rule of thumb if it's 0.1 or less. Then the sine of theta is approximately equal to theta, which is approximately equal to tangent of theta. And if you have your calculator, we are dealing with radians here. I did not put degrees here. This is radians. So if theta is, say, 0.1 radians, what is the sine of 0.1, and what is the tangent of 0.1?
0.0017.
Something's off. Oh, are you in radians or degrees?
I'm in degrees. It's 0.099. And then tangent is,
I guess 100.
yeah.
One question. The like sine of theta, and then you have like it's approximately theta, it's approximately tangent. What is that? Like, how does that help us? How did you go from there to this 0.1?
So that's the small angle approximation right there. So if theta is small,
Right.
in other words, much less than 1 radian, which is about 50-something degrees, then they're should be roughly equal. And so I said, let's just take one. Let's just take a small angle of 0.1 radian, so 5-point-something degrees. And what is the sine of it? What is the tangent of it? And the fact that these two are very close to the actual angle itself, just support for this claim.
Okay, gotcha.
At some point, if you pursue calculus, you will find that the sine of theta, there is actually a polynomial expansion that's equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial and so on. If theta is small, all these terms, the cube, fifth, so on, all those terms become tiny, and we are left with the small angle approximation. For those who get there, it's either the Maclaurin series or the Taylor series. I always mix those two up. All right, so now my equation has become negative, so if theta is small, we get negative g theta equals L alpha. I now have a direct relationship similar to this. The only difference is instead of delta x and a, I have theta and alpha. When we put them up parallel, I'll simplify, just drop the delta there. The period was 2 pi square root of m over k. This was the formula that we used earlier. Going through a very similar analysis as we did before, we would get that for the simple pendulum, the period is equal to 2 pi times the square root of, well, instead of m, it's length. And instead of k, it is g. So the longer it is, the longer the period. The greater the gravitational pull, or the acceleration due to gravity, the smaller the period. So if we're on Jupiter, that thing's going to be moving faster than on Earth. So we can actually test this out. So we need to figure out what that length is. It would be from the pivot point to where the mass is, so roughly the center of mass of that thing. Getting about 132 centimeters. So my L, 1.32 meters. Notice that the mass of the object does not come into play here. G, 9.8, or no, we'll do an actual experiment. So 9.798 meters per second squared is G. And so, period. What is our prediction for the period?
The length is going to be given in the question.
Usually, or if I told you the period, you would find the length. But,
You told us what?
so if, in this particular case, yes, we have a physical object here so we can measure the length. In a problem on a, say, a test problem or some quiz problem, typically length is given. But given period, length, and acceleration due to gravity, I have to give you, you have to somehow figure out 2 of those 3 things in order to find the third. So what is the prediction?
2.306 seconds.
All right. 3, 2, 1, go. 4. And stop. We got 5 there. So what times we get for 5?
10.88.
10.88.
I have 11.2.
11.24?
11.42.
And our average,
11.168.
and that was for 5, so divide by 5.
Yep. It's 2.2336.
We are 7/100ths of a second off. But recognize the importance of this. This is the famous story of Galileo watching the chandelier sway in church. And he came up with this idea. With the right length, because the mass doesn't matter here, with the right length, we can now have a very specific set of timing. So if I want the time to be 1 second, so for the period to be 1 second, that's going to be equal to 2 pi times the square root of some length over whatever it is in Italy.
0.25.
Okay. So if I make from the pivot point to the mass to be 25 centimeters, I now have a way of measuring not only to a second, but half of it, a half second, or from the extreme to the middle, a quarter of a second. I got timing down to a quarter of a second. And this becomes incredibly critical when you start to do motion experiments. If you want to show a relationship between velocity and position, or acceleration and velocity, time shows up quite a bit in those equations. It also has the power of if we know the length, we can actually do a measurement to try to figure out what the acceleration due to gravity is. So early experiments in acceleration due to gravity could now be done. You can now publish it. Eventually, the word gets out, and people all over the world, or at that time, probably Europe, could run these experiments and show that the acceleration due to gravity was relatively consistent everywhere. So, the incredible power of this. So, the other question before we break up here is, this assumes theta is small, but how small is small?
Is this like a limit?
Pardon?
A limit?
Yeah, except it's a little bit more nebulous than typically a limit. There's a very set number.
Okay.
So I'm hoping that with your young eyes that you can see the three lines there. There's a blue, red, and green line. The red line, the one in the middle, is the actual angle theta. The blue line is the tangent, and the green line is the sine. Notice there's a lot of overlap, especially to about there's a lot of overlap between the three of them.
Is the green one that like goes up slightly, and then the blue one's below?
No, blue actually goes up and green goes the other way. All right, so tangent goes up, sine goes that way, and the angle is straight. So, and based upon just visual inspection right there, it's hard to tell a difference between the lines that I've drawn, that are printed here, up to a little bit past 0.2 radians. So we're talking about 10 degrees. If we're looking at sine versus, there we go, using the 10% rules, assuming that 10% is close enough, you can take the angle out to just under 44 degrees. At 44 degrees, you have just broken past the 10% off barrier for the sine, theta, how close they are. 31 degrees, you're 5% off, and so on. Now, typically in physics, you generally using a 10% rule that theta is 10% of the maximum value, or in other words, 1, but you got some leeway there. On Monday, if there are no questions, and then we'll see what happens. If there are questions, how long that takes. I'm hoping to get to the point where we can predict that frequency. Have a safe weekend.